Let us consider the problem in which we have two viscous incompressible immiscible fluids which have the same density but different viscosities. The viscosity of the lower layer, so the lower layer has a viscosity equal to mu1 and the upper layer has a viscosity equal to mu2, and it is given that mu2 is less than mu1. So the thickness of each fluid layer is equal. That means that the coordinate system is located over here, and the entire flow is driven. The flow of these two fluids is driven by a pressure gradient minus dp dx. I mean, so the question is, what is the velocity profile in the two layers? Okay, so this comprises the question. So right away we assume that the flow is fully developed and everything is steady. So because the flow is incompressible, we can write del u del x plus del v del y is equal to 0. So this is fluid 1, this is fluid 2. Okay, so in fluid 1, del u1 del x plus del v1 del y equal to 0. In fluid 2, del u2 del x plus del v2 del y is equal to 0. But because the flow is fully developed, this term and this term will vanish. And del v1 del y, this will be equal to 0. And this implies v1 will be a constant. In general, it will imply that v1 is a function of x, but v1 cannot be a function of x because of this condition. So v1 is constant, and because at this surface the flow is impenetrable, then v1 has to be 0 at this interface, and hence v1 will be 0 everywhere. Similarly, from this from this condition also we will obtain v2 equal to 0. So v1 equal to 0 and v2 equal to 0. Now coming to the momentum equation. So we can write rho del ui. So this is the x momentum equation plus ui. So this I is not to be confused with the index notation. This I is for the fluid index. It can be 1 for the lower fluid and 2 for the upper fluid. Because the flow is considered to be steady, this term will vanish. So remember, for this expression, I can be equal to 1 or 2 depending on the lower layer or the upper layer. This term will be 0 because of fully developed flow. This term will be 0 because V component is 0. And this term will be 0 because of fully developed flow. Now from the y momentum equation, you can anticipate that you will obtain del pi del y equal to 0. Meaning del p1 del y equal to 0 and del p2 del y equal to 0. This is for the lower fluid, this is for the upper fluid. So if this is true, both of these imply that p1 and p2 are functions of x only, and they are also bounded by the same conditions at the boundaries. That is, whatever is driving this flow, whatever is establishing this pressure gradient, that is, there is some PL over here and some PR over here. So this entire face has that same pressure which is driving the flow, and this pressure can be generated by various means, by means of a pump. Okay, so it can be any kind of pump, but regardless of what the mechanism is, the pressure at this entire face will be fixed. That is, P is only a function of x. So whatever the pressures will be in layers 1 or layer 2, it will be the same. The velocity field will adjust itself in order to establish that the pressure distribution will be the same. Pressure will linearly fall. This implies that pressure will linearly fall from the left boundary to the right boundary. So this implies that pressure is only a function of x. So for the first fluid we can write that is for the so for y in minus h to 0, the governing equation will be dp1 dx is equal to mu1, so this will be mu I, d2 u1 dy2, and for the range y from 0 to h we can write dp2 dx is equal to mu2 d2u2 dy2. What are the boundary conditions? So the boundary condition at the lower wall at y equal to minus h, u1 will be equal to 0. At y equal to plus h, u1 u2 will be equal to 0. So now we are faced with the interface between the two immiscible fluids. What are the conditions at the interface? So this is the interface between the two fluids. So the boundary condition at y equal to 0 would be first the kinematic boundary condition of the continuity in velocity. So the continuity in velocity is a direct implication of the fact that velocity cannot have an abrupt jump going from fluid 1 to fluid 2 if the conditions are not too extreme, meaning if the Mach numbers and all are not too high, there will be a continuity in velocity. So u1 is equal to u2. So this is at y equal to 0. And we can write this boundary condition at y equal to 0 because we are assuming that the flow driven in this manner does not cause the interface to deform. So no interface deformation. Okay. So what is the other boundary condition? The other boundary condition is a dynamic boundary condition. So dynamic boundary condition means something which is derived from the consideration of stresses as we go from fluid 1 to fluid 2. So as we go from fluid 1 to fluid 2, the dynamic boundary condition tells us that tau xy, that is the stress in fluid 1, will be equal to the stress in fluid 2. Continuity of stress is a direct consequence of the fact that there is no abrupt change in shear stress across the interface. And shear stress can be continuous, but there can be a sudden jump in the normal stress across an interface. More on that in a while. So if this is true, then mu1 du1 dy is equal to mu2 du2 dy. So this is the other boundary condition. Now when can normal stress have a jump? So side note on the normal stress, if the interface remains absolutely flat, the pressure at almost the same point across the two interfaces will be equal. So if I call this 2, if I call this 1, so P1 will be equal to P2, and that's fine because the interface is flat. But if the interface deforms, okay, if this is 2, if this is 1, then the fact that the interface has deformed leads to a net a net pressure excess, that is the Laplace pressure due to surface tension. And the difference between the pressure, so P1 minus P2 will be equal to the coefficient of surface tension times the curvature of the interface. So if the interface has zero curvature, right, then P1 will be equal to P2, that is tantamount to a flat interface. But if the surface has some curvature, then this will be non-zero, and this is what you can recall from your class 11 and 12 to be the excess pressure, for example when you consider a soap bubble or a droplet of water. But anyway, in this particular case, we are considering that the interface remains flat. And the boundary conditions at a flat interface are derived from the kinematic boundary conditions and the dynamic boundary conditions. Also, the other redundant boundary condition is that at the interface there is no penetration of velocity, and that should be quite obvious that if the interface does not deform, it means there is no v component along the interface. If there was a v component, then the interface would necessarily have to deform. The v component is what is responsible for the deformation of the interface. So now let us solve this. So we can integrate this equation first, and we can obtain du1 by dy is equal to 1 upon mu1 dp1 dx times y. We can plus c1. We can integrate this once again to get u1 equal to 1 by mu1 dp1 dx y square upon 2 plus c1 y plus c2. Similarly, we can integrate this particular equation twice and get a similar result. So u2 will be 1 upon mu2 dp2 dx y square upon 2 plus c3y plus c4. And the considerations of a flat interface imply that dp1 upon dp1 dx is equal to dp2 dx. This is purely because of this result and that the interface is flat. So dp1 dx and dp2 dx we can simply replace by dp dx. That is the general driving pressure of the flow across both the two fluids. This will be dp1 dp dx, and this will also be dp dx. Remember that dp dx will be a constant. Okay, this tells us that p is a function of this, and the fact that this is only a function of x, this is only a function of y, means each of them is constant. And if each of them is constant, this means that p2 will be a linear function of x, and hence dp2 dx will be a constant. Okay, so all this follows straight from the considerations of a plane Poiseuille flow as well. Okay, so let us apply the boundary conditions. So at y equal to minus h, u1 equal to 0. So using this boundary condition, we obtain 0 is equal to 1 by 2 mu1 dp dx h square minus c1h plus c2. Using this boundary condition, we will obtain 0 equal to 1 upon 2 mu2 dp dx h square plus c3h plus c4. Using this boundary condition, we will obtain 1 upon mu1 dp dx. So we substitute y equal to 0, so this will vanish. Anyway, so this will vanish. c2 equal to c4. This is what we will obtain from this boundary condition. And finally, using this boundary condition, so if we modify this expression to be written in terms of mu1, so this gives mu1 du1 dy is equal to dp dx times y plus c1. Similarly, this expression mu2 du2 dy will yield dp dx y plus c3. Actually, this will be c1 times mu1 and c3 times mu2. So now when we find out these conditions at y equal to 0, this term and this term they vanish. So finally we will obtain c1 mu1 is equal to c3 mu 2. So this is 1, this is 2, this is 3, and this is 4. So 1, 2, 3, 4 can be solved. So we have 4 equations and 4 unknowns. This set of equations can be solved to find out the various constants. Okay, so in fact, let me just write down the solution directly. C1 comes out to be dp dx h upon 2 mu2 minus mu1 upon mu2 plus mu1 times mu1. C3 correspondingly becomes dp dx h upon 2 mu2 minus mu1 upon mu2 plus mu1 times mu2. So both of these should satisfy this additional, not additional equation, but this equation. Now C2. So C2 comes out to be, C2 has to be found out using this equation. So C2 comes out to be minus 1 upon 2 mu1 dp dx h square minus this entire thing. So minus d plus dp dx h square upon 2 mu1 mu2 minus mu1 upon mu2 plus mu1. So if I take this common, I will have mu2 minus mu1 upon mu2 plus mu1 minus 1. So this comes out to be dp dx h square by 2 mu1. So this will give minus twice mu1 upon mu2 plus mu1. So anyway, you can do the math later on at your own leisure. So finally we have the expression for all the constants and hence the equation of the velocity profile. So now the question is, how does the velocity profile actually look like? So if I consider these two surfaces, so this is y equal to 0, so this is y equal to h and y equal to minus h. This is the center line, so it will be something like this and something like this. So now what is the reason of having difference in the slope? So this is mu1, this is fluid 1, this is fluid 2. So how do you know which how the slopes will look like? So the fact is, at the interface we recall the condition, the dynamic boundary condition, mu1 du1 by dy equal to mu2 du2 dy. So if as per our original assumption that mu1 is greater than mu2, so if mu1 is greater than mu2, then so if mu1 larger than mu2, then du1 dy will be less than du2 dy. So whatever slope you will have over here, so this axis is the velocity, remember. So in order to assess the plot in this particular frame, we have to convert this into dy by du, because the slope which we typically know in the Cartesian coordinate system, okay, the slope of this curve is dy by dx. So the slope in this particular plot, that is in this particular plot, the slope will be dy by du. So don't be confused by this kind of statement and having to plot it. Okay, so the slope over here, so this actually would imply, let us see what this would imply. I mean, it's quite obvious what it will imply. It will imply dy by du1 would be larger than dy by du2, unless the slope becomes 0, in which case we cannot invert anything. So at the interface, this is dy upon dy du1, and this is dy du2. So this is dy du2, and this is dy du1, and the relationship between those two implies the nature of the slope, and the velocities are equal at the interface. So we have satisfied all the boundary conditions. So I request you to go ahead and find some time to plot this using MATLAB, GNU Octave, or whatever uh, software you like, and convince yourself this is how it looks.